Hello, everyone, and welcome to today's webinar. I'm Robin Carr, and I'll be your moderator for today's event. Thank you for being here. Our speaker today is John Bernet. John is a product and application specialist here at Fluke Reliability. As a mechanical application and product specialist, he works with customers from all industries to successfully implement their reliability programs. John has more than 30 years of experience in the maintenance and operation of commercial machinery and as a nuclear power plant electrician in the U.S. Navy. He holds a Category II Vibration Analyst certification and is a certified maintenance reliability professional. All right, you're here for Why Balance Your Machines. John, take it away.
Okay, thanks, Robin. Let's get started then. So, real quick, I'll just introduce everybody to who we are. We're Fluke Reliability, and that is a combination of Fluke and Proof Technic, Azima DLI, and e-maintenance. So we'll talk a little bit about this in connected reliability later, but let's get going. So what we're going to talk about today is common team challenges. You know, what are some of the things that everybody struggles with, and what are some of the things that we need to look at, and we'll talk a little bit about how connected reliability and balancing provide solutions for that. We'll start with talking about how to find machine faults using vibration analysis, and then we'll talk about balancing principles, how they work, and kind of the basics, and then we'll jump into how balancing, the steps of balancing, and we'll spend quite a bit of time talking about balancing. But then we're going to lead it into how it's the first step of connected reliability. So we want to talk about how this fits into the whole picture. So, and then we'll do a quick summary, and then we'll be done. So let me get started. And now that we're going along here, and I'm not going to read through this screen. I just want to show you that, hey, there's a lot of different studies that have all shown that there's a lot of issues. And there's a lot of challenges in today's businesses. We all know about, supply chain issues, workforce issues, spare parts, reduced downtime. So let's talk a little bit how condition monitoring and reliability maintenance can help us overcome some of these challenges. So first of all, let's start with everybody is on their journey to improved reliability, improved maintenance. So everybody can be somewhere on this chart, and we just want to kind of find out where you're at and where you're going. So let's talk a little bit as we go along about where you are in your journey, and then where do you want to go. So we want to kind of talk about how to get where you're going. Now, why do most teams struggle? You would think, as we've been doing this for 50 years or more, vibration analysis, we've been doing balancing for quite a while, maintenance for a while. Tools have got to the point where they're most sophisticated around, and the training is easy, and they're very, we would think that technology would be to the point where everything would be done for us. But it doesn't matter how good the technology is, we have the same problems, and those problems are time and resources. So if you look at the three main problems that all teams struggle with, it's like, how do we start a program when we're already 100% busy? We don't have time to collect route-based maintenance and generate reports and do all this analysis and trending. But if we don't have the information we need, how can we make the best decisions? Without that data that we get from our machines, we don't know when the machines are going to fail, and we can't act proactively. And the other thing is, how do we monitor all our machines within our plant when we just don't have the resources? So these are some of the challenges that we have all lived with and we're all dealing with, but we found some ways to kind of get around some of that. So many of you have already seen this, so I apologize if it's a review, but it's not like this is brand new. We've all heard about reliability and proactive maintenance. We all know that, we want the goal. We want these things. We want reliability. We want longer machine intervals. We want safer workplaces. But the problem is, then the real world comes into place, and the real world is what causes all the obstacles. obstacles. We've all heard about reactive maintenance, run to failure, which we know that isn't a way to run a plant today. We've heard about PMs, and a lot of us are probably doing PMs. When I was in the Navy, I was a PM coordinator in the engine room of a cruiser, and we did PMs on top of PMs. But every study that's been done, even back from the Navy doing a study back in the 60s, have shown that if you look at rotating machinery, failures are still 85% random. We can't use the calendar, and we can't PM our way out of this. So then we get to predictive maintenance, and everybody's heard about it. A lot of people have tried it. Why isn't it more successful? Because it's hard to change company culture, and it's hard to get started when you're already busy. So a lot of people just throw their hands up in the air and they say, well, we give up. There's just nothing we can do. Well, there are some ways to get around this, and let's talk about some of those ways. So how do some teams, how are they successful? Well, the way that they're successful is they've learned from other people. They've learned things like don't start too big and don't start too huge and don't start too complex. Start small and grow, and use the right tools and get answers. And that's one thing that you're going to hear from me many times today is get answers, not just data, and then share those answers with people on your team. We want to break down silos. We want to be able to get these answers and get them out to people. Take a look at your machines. Just buying reliability products and hardware and software we've got to look at the plant. We've got to look at the way we're doing things. We've got to look at what are our assets, what is our failure modes, what are our risks, what is our financials. There's a lot more. So it's not we got to spend hours and hours and days doing this, but let's just start small and grow, and let's start looking into a little bit more than just fixing things or doing PMs. We need to look at our resources. We need to think about what does success look like? What are our goals? How can we plan the implementation and get successful? Again, start small and grow. And then finally, don't do it alone. Get some help from somebody like Fluke Reliability or other companies that are out there. And that's what we're there for. We're there to help you pass the obstacles. And so that's what we're going to jump into next is just a quick slide of what is connected reliability? Well, basically, it's trying to simplify the solutions for people who keep the world up and running. We all know that people have certain goals, and they want to get from point A on the left to point B on the right, where you want increased uptime and cost control, production excellence. You want parts allocated, reporting. But how do you get there? Well, there's a lot of things we can do to get there. We need to pick the right things, and we need to have some help. And that's what we're here to do, is help you on those obstacles to your reliability journey from successful startup, implementation, and sustainment. We want to get a program going and show some success and show that this path does work and we can get you moving. So let's talk a little bit more about that. So what we found out is it first starts out with getting data, and not just getting data, but getting answers. And that can be done with walk-around systems, online systems, portable wireless wireless sensors. But then after we get that data, we need to get answers from that data. Just having trends or just having numbers or just having complex graphs, we're busy. We need to get answers. We need to know what's going on. And then once we know what's going on, we need to have somebody go fix it, okay? It's not going to fix itself. So we need to act on those actions, and we need to go out and perform the maintenance. And so we need to track that maintenance and keep track of, hey, why are we replacing bearings all the time? Why are we replacing seals all the time? Should that be happening? And then finally, some root cause or if we tear apart a machine, let's make sure it's balanced and aligned before we put it back in service again. Because when we tore that motor off and the pump off and did some repairs, maybe we're not aligned anymore. Maybe we're not balanced anymore. And we know that that's just not going to make it work out very well. And then finally, let's save this work in our CMMS system, and let's track this and keep things going. Okay, I'll talk a little bit more about this at the end, but basically, connected reliability helps us go through this. And instead of trying to do this on all the machines in your plant at once, start it on a small group of machines and prove that this process works, and then move on to other machines. Okay, vibration analysis. As you saw from if you saw my first slide, you'll saw that I've done some, I've learned a bit in ultrasound and thermography and vibration, but why are we talking about vibration? Well, that's really one of the easiest ways to find mechanical faults with rotating machinery. You know, they really just stand out, and it's one of our prime indicators and one of our prime tests, and so we're using it as a diagnostic tool. Now, a lot of people that aren't vibration specialists, that have heard a lot about vibration but don't really understand it, you've heard that you know, it's a great way to find issues and plan downtime, but a lot of people don't really understand really what vibration is. A lot of people think vibration is just a number, you know, that once we get to a certain number, once the vibration gets to a certain level, just like temperature or pressure or current, we know it's bad and we need to do something. Let me show you it doesn't really work that way, because if you think about it, it's dynamic like a human body. There's a lot of things going on inside your machine. There's a lot of variables. So the vibration can increase due to a problem with the machine, but also it can come from adjacent machines, the structure, resonances, cavitation, background, changing load and speed, and all of these are going to change vibration. So if we were just looking at a simple number, then, you know, is the vibration high because of a fault or because something that doesn't really matter? And so the good news is we've been analyzing vibration on mechanical rotating machines for you know, years and years and years. I've been doing this for about 35 years now, or 33 years. And I can tell you that we've learned a lot, and we can look at the patterns from all those hundreds of thousands of rotating motors, pumps, fans, compressors, and blowers. We know what imbalance is. We know what misalignment is. And so let's try to look for the most common faults. Let me also say there is no secret formula. There is no magic number. There is no magic equation. But we can learn from people that have done it before, and we do know patterns, and we do know how to look for these things. So let's use that to kind of jump into what we're talking about next. So the last thing I'm going to do here in vibration, then we'll start rolling into some of the faults about vibration, is there's really three different ways of looking at vibration. I've already talked about a simple number. Well, if you look here, you can see there's three ways of looking at vibration. Way over on the left is the very complex waveform that takes an analyst, an expert, to be able to analyze. Way over on the right is a simple number. And that's what a lot of people feel that they want, is I just want a simple number. It's nice to have a simple number. It's nice to have a number that you can trend, gives you green, yellow, orange, red, but it doesn't tell you anything about the condition of the machine. It simply says something is good or something is bad. And if it's bad, then now you have to go find out what the problem is. So when I'm in a, you know, I was electrician in a engine room and aircraft carrier for years, and I can tell you I was way too busy to be able to look at trends, and if it didn't tell me what was going on, that wasn't going to work. So the other end of the spectrum is to look at the advanced data, the raw waveform. Well, and that's too complex. You know, I guess I shouldn't say that. I mean, for a vibration expert, you can analyze it, and that's where all the information is. But unfortunately, all of that, it's like looking at a forest through all the trees. It gets lost in there. So a third way of looking at vibration is what we call the FFT, or the spectrum. This is where the patterns are hidden. This is like the EKG. So if you think about it, a pulse way over on the right, your pulse or temperature is a simple number. Way over on the left is like an MRI or a CAT scan, very complex information. There in the middle is an EKG. And a doctor knows how to look at an EKG and find out faults. And that's what we're going to do with vibration. We know the patterns for imbalance, misalignment, looseness, and bearings. So why don't we use this to be able to quickly identify those faults and ignore everything else? Because if we don't have enough time, let's just find out what's wrong. Because a simple number isn't going to tell us. So let me show you real quick how this process would work. So we put some vibration sensors on a machine, and let me show you how this does a complete circle, and then we're going to get to balancing. So you mount your sensors on a machine, or you could use a portable walk around, or you could use wired sensors. That vibration data gets sent to a gateway. It gets up into the cloud, and it gets into your database. This can also be done with a portable sensor, but we have to get some way to get this data, and this is one way to get around some of the problems of not having enough resources. If we don't have enough time to go do routes, maybe we should use wireless or wired sensors. But anyway, we get the data up into the cloud where somebody can take a look at it. And then we're going to start using some AI. We're going to start using some automated diagnostics. Remember, I told you these patterns: imbalance, misalignment, roller bearings, and looseness. We know those patterns. So why don't we sort out what's good and bad? And so we're going to trigger on what could be some possible problems, not high vibration or adjacent machines, but actual patterns of real faults. And then these are going to go to our CMMS system. The CMMS system is going to say, hey, go take a look at the data. Now, there are multiple levels of automation. I'm not going to get into this because I want to quickly get to the imbalance. But basically, we're going to find out that you have some imbalance or misalignment. So let's say that, first of all, now we have we have flagged a pattern of imbalance, and we take a look at it to do a quick check and go, oh yeah, but it's pretty slight. I'm not going to worry about that right now. So we close out the work request. A few months later, that imbalance is worse. It's not bad enough to do anything about, but let's keep a close eye on it. Months later, now it's serious. So we might want to start looking at what's our schedule and to take this machine down. And then finally, it gets bad enough that we need to go do the work. And so that's the idea of this full circle of using today's technology and fully supported by reliability experts to help us get a program going that's gonna flag us when there's a problem. We can go look at it and say, yeah, it is a problem, and then make the decision on when it's time to go do the work. Okay, so, and that's what we've been talking about with connected reliability. It's from the data, getting answers. From the answers, we get action. From action, we get savings. From savings, we get success. Right, so let's talk a little bit about faults. And how do we look at, I talked a bit about patterns. So when we look at the vibration data inside a machine, and again, I'm going to simplify this because I want to make it easy. I don't want to make it hard. If we look at the peaks inside of the data, each one of these peaks can be identified to a source inside the machine. So for example, on most rotating machinery, the biggest vibration is coming from the rotating shaft. That's this big peak right here. And then this peak over here at 4 could be that we have 4 impeller vanes. So we would first identify the sources in the data, and then we would look for patterns. The good news is we can build this information up into our software program, and it can do a lot of this work for us. So it's not like looking for these 4 faults. Even though there's hundreds of faults, let's look for the big faults. And what are the big faults? I've already said them a couple of times now, and the purpose of this course is to talk about imbalance. Why imbalance? Because number 1, it's easy to find. Number 2, it's very common. And number 3, it's the thing that's going to cause us a lot of problems. So let's talk a little bit about imbalance. So what is imbalance, or a lot of people will call it unbalance. And so imbalance or unbalance is pretty easy to find. So if we think about imbalance in a machine, let's take a, I'm not gonna, make a vibration expert out of everybody, but let's go through this and show you real quick what we're talking about here. So if you, and I'm not gonna get really high into it, but if you look at this rotating shaft right here, you can see that there's a heavy spot. You see that red dot, and every time this red dot comes around, this imbalance, we're going to see this outward force on the machine, or on the bearing of the machine. That imbalance is just like at your tire, on your car. When you go balance your tire on your car, they're doing the same thing. They're finding that heavy spot, and they're correcting that heavy spot by putting a counterweight on the other side. So from vibration, we're able to find and diagnose imbalance very easy. It's a very common fault. So it's going to be a high vibration at the speed of the rotating shaft, and it's typically in the horizontal and the okay, I'm back. Sorry about that. So, and again, we're gonna make these slides available to you. So if I go through something too fast, then don't worry about it. Here's another way of looking at it. Now, I'm going to use misalignment, but imbalance has the same type of a pattern or tracking. So whether the fault be imbalance, misalignment, bearings, or looseness, we can track these faults. When I was in the Navy doing vibration analysis on machines on an aircraft carrier, we would track faults 12 or 18 months in advance. We'd watch it go from slight to moderate to serious to extreme. And so this would be over months. So if you look down here at the bottom, you can see over on the left is a machine that's aligned, and you can see that the overall vibration, the blue line, is showing a trend, but it's pretty flat. And if we look at the spectrum down at the bottom, so again, the overall vibration is all the vibration, and then down at the bottom is the FFT, or the trend, that's showing us the individual peaks. And so you can see that this is what a healthy machine is. You can see that in a few months, the overall vibration is increasing, but that could be from just about anything. But down at the bottom, you'll notice that the pattern doesn't look the same. Notice that the second harmonic is higher than the motor vibration, which seems a little bit weird. That doesn't seem normal. And then finally, way over on the right, we see that the overall vibration has peaked very high, and now we're seeing a lot of things going on. So this is how we would track a fault, is by knowing the pattern and watching this pattern get worse, we're able to determine that, hey, it's time to fix this machine. So let's jump to about why are we interested in imbalance and misalignment? Well, when I've talked to teams over the years and I ask them, what are your problems and what kind of things are you having wrong with your machines, they almost always say bearings and seals, bearings and seals. Well, the thing is if you replace the bearings and seals, that's not the problem. The root cause is imbalance and misalignment. And so you can see here that if we just keep replacing bearings and seals, we're not really fixing the root cause, we're fixing the symptom. So we need to first determine what is the root cause. How? By going to the vibration. If we take a vibration reading, we can identify, is it imbalance, is it misalignment, and is it looseness and bearings? So first, let's go find out what the root cause is. And then second, let's fix the problem. If a machine has imbalance or misalignment, then let's not leave it in that condition and just keep replacing bearings. Because when I was in the Navy, that's what we would do. We would just keep replacing the bearings, and the mechanics would replace the bearings and the seals and the pumps. We'd put it together, and then it would go all over again. It wasn't until we started balancing and aligning machines that bearings and seals lasted for years and years. So that's what we're talking about here, is we need to fix the root cause, and that's why balancing is the first step of a connected reliability program. So again, there's a lot of text here, and we'll send you this, and many of you already know what imbalance is. But if you think about it, it's a heavy spot on the shaft, you know, and if it's just simple imbalance, you'll just have one heavy spot, but you could have two heavy spots that are completely 180 degrees away from each other and could make you feel that this machine is balanced. And it isn't until you get the machine up to speed that you start feeling the wobble. So we'll talk a little bit about that imbalance. But again, as we've told you before, it's that you know, centrifugal force as the shaft rotates around. So that leads us into static imbalance and couple imbalance. So just like I showed in the previous, if we just have one heavy spot on the machine, then that's static imbalance. Couple imbalance is where you have two heavy spots and they could be countering each other out. And so this is what determines if you have a single plane of balance or a two plane balance job. Again, I'm not going to get too much into that because we just have a simple webinar to introduce this and talk a little bit about it. Where does imbalance come from? Well, it could be from the initial design of this machine or construction. I mean, it could have been built with uneven mass or the windings of the motor, or it could have been built that way. It could be faults. I mean, we could have some material fatigue, we could have some erosions, or we could have some buildup. It could be mounting errors. I mean, you could have some imbalance because of the way that the bearing seats were machined and you know, that kind of stuff. Or it could be operational. We could have a buildup. So you could have like this fan blade over here on the right. If you have a buildup that's uneven on your fan blades, it's going to give you imbalance. I thought I might have had something there, but let's just keep going. So why is shaft balancing needed? Well, if you don't have a balanced shaft, then your performance is going to be down. We're going to wear your bearings and seals. You're going to have more of an energy drain. You could be losing thousands of dollars of replacement bearings because you're not balancing your machines. So balancing your machines is very important. So let's talk a little bit about some of the benefits of precision balancing. And also, we want to do this on a majority of our machines, not just a few. I was having a little bit of a slow reply on my video, so I turned it off, but it looks like it's working again. So let's just keep going. So what are some of the benefits? Well, I'm going to go through these pretty quick, but you know, 50% of damage to rotating machine can be directly related to imbalance. A lot of people go, well, that math doesn't work out. You know, if you're saying up to 50% is imbalance and 50% is due to misalignment, what about my bearings and looseness? Well, that's because it can either be one or the other, or really, if you think about it, the real damage is coming from the imbalance and misalignment. The bearings are probably just a byproduct of that. So again, let's not get into all the numbers, but why do we want to do precision balancing? Well, it extends the life of the machine, less wear, lower temperatures. We all know why we want to do it. A balanced machine is going to run longer. Oh, power consumption. If we run a machine that is even a little bit imbalanced or misaligned, it's not going to be running as smooth, and we're going to see problems. Okay, field balancing. So some things that we're going to think about when we're looking at our balancing equipment is, you know, one of the pain points that we want to reduce is we want to reduce vibration levels, but we really want to reduce our failure of our machines. You know, we want to reduce catastrophic failure of machines and bearings. And if we have a lack of experience of our teams, then we need to get some tools that are going to allow us to make balancing easy or simplify it for us, and make it fast and easy, because that's been the problem. If imbalance is difficult, if imbalance is time consuming, then people won't do it. You know, if you have an imbalanced machine, you'll just live with it. But the problem is living with it is not a good solution either. So let's find a way to find out that we have imbalance and then get some quick and easy tools that are going to help us be able to balance the machine. So how do we do balancing? Well, there's different programs on the market, but the most common and most traditional, the one that I've used in the past and the one that most people use, is called an influence coefficient method. And basically what we do is we put on a weight and we record the angle and the amplitude. So we put a weight on there that's going to put it a little bit more out of balance, and by seeing the phase angle of the imbalance and the amplitude, then we can determine, oh, if I've influenced the imbalance by this much, by this many degrees, then that means it's probably here. So then you would put a weight on there. So we do an initial run, then we do a trial run, and so basically it's just like the same as the tire on the wheel. You put on an influence weight that moves the imbalance. That allows you to calculate where the imbalance is. Once you know where the imbalance is by using a polar plot, then we can calculate how much weight to put 180 degrees out. And then we do a run and we find out if we fixed it, and we might have to do some trim runs to make it a little better. So here you see the process using some screen captures. So the initial run is where we're going to start the balancing procedure, and we're going to take our initial measurement. Then we're going to put a trial weight somewhere on the shaft or on a fan blade, and we're gonna use that as our reference point. We're gonna call that our 0 point. Then we're gonna take a run with that trial run, and on that trial run, we're gonna look at our vectors and see what angle and how much it moves by, and then we're gonna say, oh, based on doing the math and looking at the vectors, I put this much weight on and it made it move this much. Then if I put this much of correction weight on at this angle, I can correct it. So then you do a correction run, and you do as many trim runs or correction runs as you need until you get it into balance. Okay, so we've gone through the balancing. Went through it pretty fast. If you want some more information about that, we'd love to talk to you about it. A lot of different people are using this technology and this tool. The last thing we're going to do to wrap this thing all up is let's talk a little bit about how this all works with connected reliability. And the first step of connected reliability is making sure that we install with precision. So we're going to talk through each of these real quick. We're going to talk about installing, acquiring, enriching, acting, and then all of this connected. So if you look up at the top, you can see a machine failure curve. And by using vibration and thermography and ultrasound, we're going to be able to find out when a machine is starting to have problems. We don't want to wait until it gets over to the hot to the touch or about to fail. And by using precision alignment and balancing, we can move our curve and we can make it a little bit, we can move it over to the green area and get more life out of our machine. So what I'm saying is, let's try to start in the best position we possibly can, and that's by precision alignment and balancing. So by precision aligning and balancing, we're putting the machine already in a better position, and that way it's going to last a lot longer, parts will last longer, and we'll have fewer failures. If you're already starting from a point where the machine is misaligned or imbalanced, then you're going to have a lot less life before you get to the point where it's time to repair that machine. Okay, so we've talked about the initial installation is let's align and balance machines. Then the acquisition time. We need to collect some data. There's a lot of different tools. There's vibration tools, there's alignment tools, there's ultrasound tools, there's balancing tools, a lot of different tools that we're going to use, handheld tools, wired tools, wireless tools. And so basically, and there's, like I said, different types of tools. And so let's figure out what tool, but we've got to do something because we've got to get data. Without data, without answers, we don't know what to fix. So that's getting good data from our machine. Now, once we get that data, we have to enrich it. What do we mean by that? I need to get answers, okay? I don't have time to look at a bunch of simple green, yellow, orange, red. I don't have time to look at complex waveforms. Sometimes you do. Sometimes the machine is complicated enough that I'm going to have to get deep into it. But a lot of the simple motors, pumps, fans, compressors, and blowers, I just need to know, what have I got to do to fix it to get it up and running again? So that's what we're talking about here is let's get answers from that data, and that way we know what to do. And that enrichment depends on the type of machine, the complexity of the machine, and what kind of faults you're looking for. Okay, act. What do we want to do next? Well, based on the information we have, we now need to act on that. And that means that we need to get some work orders. We need to get some repair recommendations. We need to find out if there's parts. So this is where we start empowering our teams. We need to start talking to people and say, hey, we've determined this machine is imbalanced. We need to go out and balance this machine. So I need to generate a work order to have somebody go out and do some work on this machine. So we need to act on that based on what you found. And then finally, we're going to talk about, you need some knowledge, and we need to be able to get some assistance, some information. And so there's training, there's active assistance where we can have somebody come in. So we can have some people come in to do some services. We can have people come in and set up remote condition monitoring for us, and we can do some on demand. So we don't have to get training continuously. So we might want to get some consulting, or we might want to get some training of our team. Okay, so we've talked about a lot of things over the past 40 minutes or so. Actually, I guess it's a little longer than that. I'm trying to look at my clock here, but what have we been talking about? We've been talking about maintenance teams that are struggling. The business challenges that you're having, everybody's having the same issues. It's all a lack of resources. It's maybe not having enough skills. It's not having vibration experts. So we used to have vibration experts. It's a lack of resources. Mainly, it's a lack of time. We just don't have the time to do what we need to do to cover all the machines. And sometimes we don't have access to our machines. And sometimes those issues are compounded. So condition monitoring allows us to take vibration readings from machines, find out what the faults are, and then most importantly, go use tools like balancing tools to correct and bring the machine back into service. So precision balancing alignment are the first steps of connected reliability. And I think we've shown you there as kind of at the beginning and then almost again then at the end. And so make sure that you find a partner that can help you, that can walk you along your journey and get you to a point where you're being more proactive about your machines instead of just replacing bearings and seals. Okay, I think that brings us to the end, Robin.
John, can you hear me?
I can. Hi.
There we are. I thought I lost you for just a second. Thank you so much for your time today, John. We appreciate you joining us today and look forward to your next presentation at a Fluke's Best Practices webinar.
All right. Well, thank you very much.
Thank you, and talk again soon. Thank you.
Take care. Bye-bye.